Welcome back to our course on memory device technology for AI/ML computing. I'm your instructor, Dr. Shubhadeep. So let's have a quick recap of what we were studying the last time around. We were looking at the erase and read operation at the cell and array level. So in the erase operation, we saw that how instead of applying minus 20 volts at the control gate to eject electrons from the floating gate, we apply plus 20 volts at the substrate. This has a reason from the array level because we want to do erase operation at the block level, and hence this is where the name flash comes from, right? And what we essentially do is we make sure that the substrate connection to all the cells in the same block are the same. So we apply 0 volts at the control gate of all the cells, and at one shot we apply plus 20 volts at the substrate, and all the cells get erased. But it takes little significantly larger time of close to 1 millisecond. In the read operation at the cell level, it is all about selecting the appropriate read voltage at the control gate. As you can see, the appropriate read voltage at the control gate lies at the midpoint of the threshold voltage at the erase state and the threshold voltage at the program state. Okay, so here erase and program had minus 2 volts and plus 2 volts threshold voltage. So that is why we selected read voltage to be at a 0 gate bias, right? After that, what you do is you apply a small drain bias and see whether the transistor is in on state, then it is an erased condition, or is it in the off state, then it will be in the state 0 or program condition, right? So this is what we saw. At the array level, what we do is in addition to applying the read voltage for the page of interest, remember, just like program operation, read operation is also done at the page level. So what you do is you apply read voltage at the page of your interest. You apply a pass voltage at other word lines, so that irrespective of state of the cell, it allows your small bit line voltage that we apply, which is to be finally passed on to the drain of the transistor of our interest, to allow that to pass through. That's why it is called the pass voltage, which is applied at other word lines of the block which are not of our interest. Once we do that, depending on whether there is a discharge of the bit line or there is no discharge of bit line, we can either detect the erase state or the program state, because the erase state will allow for a string current to flow because it will be in low resistance state, whereas at program state it will not allow the string current to flow. So by checking whether the pre-charged bit line is discharging or not, we detect either a erase state or a program state for the page of our interest. Okay, so with this we finish the fundamental operations and understanding both at the cell level and array level for all three important operations. Remember, they were program, erase and read. Next, we are going to look at the technological aspects of NAND flash. What really makes NAND flash technologically so special in terms of high bit density storage technology. We have already discussed the two aspects are bit scaling and vertical scaling. Vertical scaling is the transition from 2D to 3D NAND flash. So today we begin with bit scaling. So the idea of bit scaling from single level cell to multi-level cell is pretty much a simple idea. In principle, it's a simple idea. The idea is, can we improve the bit density and therefore the cost per bit by cramming in more bits in a cell? Okay, but of course, like anything, there will be very important challenges. So let's discuss the challenges that we will face in doing this. The expectation is very simple. It's, I would say, a bit too simplistic or too naive to go from SLC, which is a single level cell, which has just one bit or two different levels. So here we can see two levels, the erase state and the program state. So two levels means you can store only one bit. If you want to transition to, let's say, the next level, which is a 4-level cell, through which you can store 2 bits, because 2 to the power of 2 is equal to 4. The simple way of trying to do that would be to have intermediary states and intermediary threshold voltages in your cell. So for example, this was the erase state in our example was -2 volts, the threshold voltage, and the threshold voltage at program state was +2 volts. So the idea is, if we have two more transfer characteristics, one with -1 volt and one with +1 volt, we will have equally spaced states. If we have equally spaced states, you will be able to store 4 distinct values instead of 2. So this is possible by introducing or injecting different number of electrons into the control gate. For example, if the program state had 3x electrons, x can be any number. Let's consider it to be 1000 for the time being. So if there were 3000 electrons which shifted the threshold voltage from erase state of -2 to program state of +2, since the threshold voltage is a linear function of the trap density, what you can do is, by filling in x number of electrons, you will be able to shift it 1/3 the distance or 1/3 the gate voltage, and by filling 2x number of electrons, you would be able to move the threshold voltage 2/3 of the distance. So this is a very simple idea. This is a simple, but as I said, it's a naive idea. What actually happens in reality? What actually happens in reality, if we only look at a 2-level cell or a single, or my apologies, even if you look at 2 states, which is a single level cell, you will see that your devices suffer from large C2C and D2D variability. What is the meaning of C2C and D2D variability, which we will keep using multiple times? C2C means cycle to cycle variability. Here, the variability that you see when you keep programming and erasing the device again and again is called the C2C variability. D2D variability is device to device variability, where you see variations in the transfer characteristics of the device or any performance metric of the device from one device to the other in the same array. Okay, so there are large C2C variability and D2D variability, and this occurs primarily because of process and manufacturing defects or variability. As you know, any process that happens will not be exactly identical. So there will be some variabilities either in the material or in the manufacturing steps, in the geometrical considerations, however stringent you try to make them. So this will introduce cycle to cycle and device to device variability, which I have indicated. So in this graph, what I have indicated is not just one best value or one mean value of the threshold voltage, but I have collected the transfer characteristics both at erase and program state for multiple cycles or multiple devices. And as you see, this is not just one threshold voltage, but there is a band of threshold voltage, both for the erase state and for the program state. And the best way to represent that is using the probability density function. So in the probability distribution function, the x-axis is the threshold voltage of your transistor or the cell, both at the erase state, state 1, and the program state, which is state 0. The y-axis consists of the counts, the number of times in every cycle or in every device that you get the particular threshold voltage. So when you plot all of them together, if you start extracting the threshold voltage from each of these curves, you will see you get something like a semi-hemispherical curve or a semi-spherical curve, sometimes it can also look like a Gaussian. The shape of the curve for the moment is not very, very critical for us. Okay. And when you do it multiple times, you get these probability distribution functions, which has a particular mean. Mean is the average value at the erase state, and the mean for state 0 is the average value at the program state. But also, as you can see, there is a significant deviation or standard deviation in both the states. So there is a significant standard deviation in both the states. So it is not enough to look at just the best values or mean values. You also have to worry about the standard deviation. Why do you have to worry about the standard deviation? Because you have to ensure that the maximum threshold value at the erase state has to be significantly lower or significantly less compared to the minimum value in the program state. Or in other words, there has to be a sufficient margin between the state 1 values and state 0 values to do an effective read. And therefore, such kind of variability characterization is absolutely crucial in knowing what should be the actual read voltage. Not just the read voltage. Remember, in the last class, I asked you what should be the appropriate pass voltage at read condition that we apply to other word lines other than the page that we are reading. So the consideration for pass voltage was that irrespective of the state of the cell, it should allow current to flow through. So that's why the pass voltage is kept with a sufficient margin from the highest threshold value of state 0. So the point I'm trying to make is variability characterization is very important to decide the biasing conditions to ensure sufficient margin between the two states. Now, with this understanding, it will be much easier to understand the transition from SLC, which is your single level cell, which we have been dealing with till now, which has just two states, state 1 and state 0, to MLC. What is MLC? It is called multi-level cell, but in fact, it has 2 bits that get stored. So you have 4 states or 4 distinct threshold voltage values. On to TLC. TLC is a 3-level cell. In a 3-level cell, as you can anticipate, there will be 2 to the power of 3 or 8 distinct states or 8 distinct threshold voltage values, as you can see in this particular graph. Next, we move on to from TLC to QLC. QLC is a quad level cell, or 4 bits can be stored in the same cell. So you will have 2 to the power of 4, which is, so there are 16 digits or 16 different combinations of ones and zeros that can be stored in the QLC. The first thing to notice under the context of maintaining sufficient margins between the consequent states or neighboring states is that it is very fascinating to see that as you move from SLC to MLC to TLC to QLC, the space or the margin between the states is becoming to shrink significantly. As you can see, in SLC, there was a significant gap between the 2 states, which has become much smaller when it gets to MLC, gets even tinier when it comes to TLC, and is almost non-existent when it gets to QLC. Okay, so when the margins become much smaller, you have to understand that when you program and erase these particular states, especially when you program these states other than the erase value, other than the lowest threshold voltage value, you have to be very careful. You need a very tight control in the threshold voltage programming. How is this done? We will see later on in this very lecture. The second important thing to notice is that the encoding, the encoding of the bits is non-trivial. What do I mean by non-trivial encoding? Let's see with the example of the MLC. The threshold voltage which has the least value is in erase state, followed by the 0 1 state, then comes the 0 0 state, and then the 1 0 state. So you see, you have 1 1, 0 1, 0 0, and then 1 0. This is not what you would generally expect. You would expect 1 1, 1 0, 0 1, and then 0 0. Why have we shuffled up the bits to have such non-trivial coding? If you notice very carefully, you would see that among adjacent states, the bit values are separated by a Hamming distance of only 1. This means that every state, every neighboring state, the only one bit changes. Okay, this is very, very helpful to minimize the error rate, because if there is any shift of Vt from one level to the other because of the broadening of this distribution or because of any error in reading, it will only result in one bit error. Okay, so this is very important to note, and that is why you see even in the TLC and in the QLC, when you go from one state to the neighboring state, you will see that there is only a Hamming distance of 1. Okay, the third thing to notice is that the read operation will become very, very complex as you move from SLC to QLC. Why is this the case? Because earlier you just had to read whether the transistor is in on state or off state. However, when you go to MLC, you will have 3 other read threshold voltage conditions or 3 other currents that you would want to detect. So how this is generally done is in form of a binary tree search. So what you do is, first you check the the least significant bit, whether the least significant bit is 1 or 0. If the least significant bit is 1 or 0, how do you find out? You find out by checking what is the state of the transistor at the middle read voltage. Once you have figured out whether the least significant bit is 1, then you go to the next threshold voltage and figure out whether the most significant bit is 1 or 0. So this happens in form of a binary tree search, and therefore read operation from the peripheral circuitry becomes very complex, because now there are several read currents for different threshold voltages. Just like read operation becomes more complex, you would also anticipate that programming operation will also become more involved, and this will result in significant amount of latency when we move from SLC to QLC. And this is what we have indicated in this particular schematic, that as you move from SLC to MLC to TLC to QLC, you get an advantage of bit density and therefore cost per bit, because in the same footprint where you were first able to store only 1 bit, now you are able to store 4 bits. So this is the advantage, or this was the primary motivation of moving from SLC to QLC, but there are significant amount of trade-offs. The first trade-off is that in performance suffers when you move from SLC to QLC because of the read latencies. Read process becomes much more complicated, and also program latencies, as we will see very soon in this lecture itself. Also, the other thing that suffers a lot is reliability. Why does reliability suffer? For the same reason that you are not now keeping enough margin between the adjacent states. So there is a significant probability that there will be the merging of states, which will cause a lot of read and write errors. Okay, so it is, as we know in life, there are no free lunches. When you try to improve the cost per bit, you suffer in terms of reliability. And you would be very surprised to know that SLC, which is a more simpler technology, is actually used for high performance applications because the latencies are very, very low, whereas QLC and TLC is used in low end products, which are a bit more cost sensitive. So with this understanding of trade-offs, let's move on to the final discussion of today. How do you achieve such fine control over VT to program these QLC, TLC and MLC? Just like read process becomes complex, even the program process, which is used to gain fine control over VT so that you can cram in more number of bits or more number of states within the same cell, is also a very interesting process. And this process is called incremental step pulse programming. So let us understand incremental step pulse programming with a very simple use case. Suppose I have several cells which are there already in the erase state. How do I design a pulsing protocol such that I can reach my target VT? So common sense would suggest that I start with a very small voltage, and let's start with 16 volts, just a single pulse. And what I see is that the distribution, when I do it over a lot of cells, is unable to achieve the target VT. So the next natural tendency will be to apply a pulse of a higher magnitude. So that is what we will do. We will apply a pulse with slightly larger magnitude of 18 volts. And what we see is, although we are able to achieve the target VT, it comes at the cost of a much larger standard deviation. This is common sense. If you apply a larger force on a particular object, the displacement or the variability in the displacement will also be larger. So what I do is, instead of going from single pulsing protocol, what I go to multiple pulsing programming protocol with the smaller amplitude. So apply 20 to 30 pulses of 16 volts, that I see that I am able to reach my target VT with reasonable amount of standard deviation. But the problem is, I have to apply around 20 to 30 such pulses. This pulsing scheme comes with the problem of high latency. So the question people started asking is, can we think of a pulsing scheme which has both low variability and low latency? And this is where the ISPP program becomes very handy. It becomes very useful. Through this very simple schematic, I have tried to explain to you what is your ISPP. So the first feature of your ISPP is that it is not just program cycles. There is alternating program and verify cycles. What do I mean? That you apply one voltage or one large voltage of program. Here it happens to be 16 volts. You don't apply the next program voltage immediately. You do a verify. Basically, the verify means you do a read. So after doing the program, you check what is the current threshold voltage value and whether it has reached the target threshold voltage value or not. If you want to understand it from this example, you would see that you apply a pulse of 16 volts, then you check what is the threshold voltage of the cell that you have programmed. So if you see that the threshold voltage is less than your target threshold voltage, you proceed on to the applying the next pulse, which is slightly more. That is where the word incremental step comes from. So instead of applying again 16 volts like we did in this particular example, you apply slightly more, which is 16.5 volts. And this process continues to 17 volts, 17.5 volts until you reach your target VT value. Can we think intuitively why doing ISPP really works? Just take the example of blowing into a tire or blowing into the balloon. The first time you blow into a balloon or a tire, it is initially very easy. But consequently, you have to work harder into filling air into the tire. This is because the elasticity of the rubber in the balloon takes over and it tries to prevent more air from coming in. Similar is the case even for a floating gate transistor. There it was the elasticity. Here is the Coulombic repulsions between electrons which are confined into a small space. So initially it is very easy to put the electrons into the floating gate, but to reach the target voltage you have to keep applying incremental steps of more and more amplitude. Okay, and this is what we see when we apply incremental step pulsing. It gives you a lot of benefits. The first benefit that you see is, compared to cells which have been programmed with just fixed voltage, ISPP gives you very tight distribution. It gives you a very tight distribution, as you see from this blue curve. When you have only fixed biases, the sigma or the standard deviation of the distribution is very large. With ISPP, you reach the target voltage very, very quickly, and you reach and with very low standard deviation. The other thing that we notice is that ISPP is able to manage variability in a much better fashion. What do I mean by manage variability? Here we have indicated two kinds of cells. One is a fast cell and another is a slow cell. What is a fast cell? A fast cell is a rubber balloon which fills very easily. So a cell where with very little inputs itself, you are able to reach the target voltage. Whereas a slow cell takes several more cycles or several more pulses to reach the target voltage. And this is of course because of the variability in the cells. Also, what people have noticed is that against the fixed voltage protocol, where you took almost 20 to 30 pulses to reach your target voltage, your incremental step pulse programming helps you in reaching your target threshold voltage just within 3 to 7 pulses at a much tighter VT distribution that we have already discussed. Okay, this is in crux what the ISPP protocol is all about. To conclude today's lecture, we will see how ISPP is implemented both in MLC and TLC cells. So the actual practical programming from the erase state to the intermediate state takes a very staged programming protocol. You don't directly jump from erase state to 4 distinct states. So let's see this with an example of 2-step programming protocol for MLC. As you can see in this schematic, the first step, the flash cell is partially programmed based on its most significant bit, either in the erase state, it will either stay in the erase state, or if the MSB is 1, it will move to a temporary state. What I mean is, you have a bunch of cells in erase state. Depending on whether the MSB is 1 or 0, it will go to, it will either stay in the erase state, or it will be programmed to go into another temporary state. Okay, we will see what will be the threshold voltage of this temporary state. It will be between the next consequent states that it will be programmed to. So in the second step, what we do is the MSB data is first read back into the internal buffer register of your external peripheral circuitry to determine what should be the cell's current threshold voltage, and then further programming pulses will be applied based on the least significant bit. Now, depending on this X is 1 or 0, either you stay in the erase state or you move on to the first programming state. If the state to be programmed is P2 and P3, you start from the temporary state and move on to the P2 state or the P3 state. Okay. A similar but not exactly same multi-stage protocol is even used for TLC. So in TLC, the protocol is slightly different. There is 3-level programming. First, you start from the erase state. From erase state, you move on to the temporary state, or you stay back in the erase state. Now, depending on what would be the final value, whether it will be P4, P5, P6, P7, you tune the temporary state or the temporary programming state into 4 different threshold values. But this initial programming is called foggy programming because you don't do a fine tuning of your threshold values. You just do a very rough programming, but this will have a lot of errors because you can see there is very little margin between adjacent states. So in the final step of fine programming, what you do is you allow enough margin to exist between the adjacent states. So as you can understand, just like the read operation becomes much more complex with going from SLC to QLC, the programming complexity also increases, and therefore there is a significant amount of latency. For example, your MLC is around 200 microseconds per page, TLC is 500 microseconds per page, and QLC can go up to 2 milliseconds per page. This is consuming much more time compared to SLC, which can take only 10 to 100 microseconds per page. So there is a distinct trade-off between integration density and latency. And as we had discussed earlier, that SLC is used for more high-end, high-performance applications, whereas MLC, TLC, QLC is used for more cost-sensitive applications. This concludes our understanding of bit scaling in modern day NAND flash cells. In the next and concluding class of NAND flash, we will look at vertical scaling, the transition from 2D to 3D. What were the scaling challenges which inspired us to innovate and transition in the vertical direction from 2D to 3D. Thank you very much for your kind attention. Let's meet in the next class.